Hello students, welcome to Inside Physics. In this session, we are going to learn about binding energy of a nucleus. We all know atoms contain nucleus. So this nucleus is a central part of the atom. So the more interesting features in this session you are going to see in the next 15 minutes. So here binding energy is an absolute interesting concept of the lesson nuclei. So, nuclei is a plural to the word nucleus. So, all the atoms, molecules, and ions are having a central part of nucleus. So, here, before going to the binding energy concept, we will see some relation between mass and energy proposed by the great scientist Einstein. So, mass energy has a relation. How? Prior to the theory of general relativity proposed by Einstein, it was assumed that mass and energies are considered as separate entities, and in the chemical reactions and other proportionate reactions, it is considered that mass and energy are conserved separately. Okay, but after the theory of general relativity proposed by Einstein, it was successfully explained by him that we can convert mass into energy and energy into mass. So he has proposed an equivalence relation, which is a very famous relation, Einstein's mass energy relation. So where m is the mass of the object or material or atom, c, this is the speed of light. We all know the speed of light is around 3 to 10 to the power of 8 meters per second. So this is the equivalent mass energy equivalence relation. Okay, now we see how the mass and energy are related with this equation. So there is a proposal from Einstein that the mass must be converted into energy. So now how does this have a relation with binding energy? First of all, we have to know what are there inside the nucleus. We all know that the constituents of a nucleus are they are called nucleons or protons and neutrons. Protons and neutrons. Protons are positively charged and neutrons are electrically neutral. So here we have a concept of mass defect. So here whenever we take an atom, it must have some mass. Okay, and for that calculating the atomic mass, theoretically we have a concept of having calculation of atomic mass, and the units for calculation is AMU, 1 atomic mass unit. This is also called or 1 unit. Okay, this is what we take for the calculation of atomic mass. So here what is the value of 1 unit? So what is the definition of actually 1 unit? It is the mass of 1/12 of the mass of carbon atom. Okay, so the value of 1 unit is 1.660 into 539 to 10 to the power of minus 27 kg. Okay, So here the unit is taken to calculate the atomic masses or the masses of subatomic particles. See, how we get this means, if you consider the carbon atom mass and you divide the mass of the carbon atom by 12, you will get this value. So this is also called 1 AMU. Now with this, or 1 unit, with the help of this value, we are now going to see and calculate the mass of oxygen atom theoretically. We'll here oxygen 816. Okay. Now there are 8 electrons, 8 protons and 8 neutrons. This is atomic number, 16 is the mass number. So how many electrons and protons are there? 8 electrons and 8 protons. If you subtract this atomic number from mass number, it will give the number of neutrons, A minus Z. Okay. So these electrons, protons and neutrons are contributing towards the mass of the oxygen atom, that we know. But compared to protons and neutrons, electrons have very negligible mass, right? So we can exclude these electrons when we are calculating the mass of an atom. Why we can exclude means, this is having a very negligible mass. Mass of an electron is 9.31 into 10 to the power of minus 31 kg, and when we compare this with the proton, which is nearly equal to 1.66 into 10 to the power of minus 27 kg. So almost this is 10 to the power of minus 4 times lesser than the proton. So when you are calculating the mass of an atom, the contribution is from protons and neutrons, most of the contribution. That means these protons and neutrons are in the nucleus. So we can say 99.9% of the mass of an atom is contributed by the nucleus. Okay, now we try to calculate the mass of this oxygen atom theoretically by considering the unit AMU. So here 8 electrons, 8 protons plus 8 neutrons. So we will take the mass of electron, proton and neutron in terms of AMU. So here I have taken the values here. So no need to remember, just we can take the values and we can substitute in the in calculating the oxygen atom mass. So we can say that there are 8 protons, that means 8 into mass of proton. So 8 into that value 1.00727. So here again mass of neutron 8 into 1.00866, because the mass of neutron is slightly greater than mass of proton, and there are 8 electrons also. Mass of electron is 0. Very less. You can see there 8 into 0.0055. These are all units. One taken in the units as AMU, or you can simply write U. So now what is the mass of the atom? Theoretically we can consider that the nucleus is the major contributor. So we can take these two values. So if you sum the mass of proton and mass of neutron, if you sum 1.00727 and 1.00866, you will get a value. I have noted there 2.01593. Okay, so this will be around 16.12744 units. Okay, so this will be 16.712744 units. So what is this? Mass of nucleus of the oxygen atom. Okay, now here if you want to calculate the masses of any atoms or ions, you can have the experiment called spectroscopy, mass spectroscopy, where you can exactly calculate the actual mass of the atom. This is theoretical mass of the nucleus, and when you are calculating the actual mass of the oxygen atom by mass spectroscopy, you will get this value. So actual mass of oxygen atom with the help of spectroscopy is come to be 0.99493 units. This is the mass of the atom. So we need to exclude this the mass of electron from this. We need to exclude the mass of the electrons from this. So how to get the mass of nucleus by excluding the electrons means simply you can calculate 8 into 0.0055, which is this value. This value is subtracted from this value. So actual mass of here, this is atom, per atom. So when you subtract this value, the electron mass from this, you will get the mass of the nucleus of oxygen atom. Here I have mentioned the value. So if you calculate, we go to the calculations, it will take some time. So that's why I already mentioned the values so that we can move on with the explanation. So this is the mass of the nucleus of oxygen atom, actual mass. This is theoretical mass. This is of nucleus. So there is a difference. If you observe the difference between the theoretical mass of the nucleus and actual mass of the nucleus. Okay. So why this difference has come? That is the fundamental concept to enter into the concept of binding energy. There is a difference in calculating the mass of oxygen nucleus with actually theoretically and the actual mass with spectroscopy experiment. There is a difference. This value and this value, when the difference is here, I mentioned the difference. What is the difference? It has come out to be 0.13691 units. Okay, this is the difference between the theoretical mass of the oxygen nucleus and actual mass of the oxygen nucleus. Why this difference has come? In this session, we call this difference of mass as mass defect. Mass defect. So this mass defect is nothing but the difference between the theoretical mass and actual mass. So this is the mass where it actually disappeared while forming the atomic structure, and also when the nucleus is actually at the center of the atom, and all the protons and neutrons are tightly bound inside the nucleus. What is the reason? In spite of having the Coulombic repulsion force between the protons, the force is the Coulombic force must be overcome by another force, otherwise the nucleus will not be stable. So here this mass is converted into energy. See, the formation of the nucleus, that means the protons and neutrons are confined to a very small space. What could be the radius of the nucleus? It is around 10 to the power of minus 15 meters. Such a small confined space. In this space, all the 8 protons and 8 neutrons of the oxygen atom are placed in the inside the nucleus. So this mass difference, that is called mass defect, has changed into energy, and this energy is actually creating some force. Energy, whenever we spend energy, it is creating a force. That force, actually called nuclear force, will be binding the protons, overcoming its Coulombic repulsive force between two positive charges. This force is called nuclear force. Okay, so how to calculate the mass defect? What is the mathematical relation to calculate mass defect? Before that, we see how the Einstein's mass energy relation is worked out when we take some 1 gram of mass, and how much is the energy released when 1 gram of mass is converted into energy as per this relation. 1 gram, we are taken m as 1 gram, that means to convert into kg, it is 10 to the power of minus 3 kg into c, velocity speed of light, it is 3 into 10 to the power of 8 whole square. So it will come around 9 into 10 to the power of 13, 9 into 10 to the power of 13 joules. So this is the energy, enormous amount of energy is released when 1 gram of mass is converted into energy. What do you think? Now I am telling about the Einstein's general theory of relativity. So what do you think? Mass and energy both are same, or mass has a different definition and energy has a different definition? According to this theory of general relativity, both are interconvertible. We cannot see mass as a separate entity and energy as a separate entity. So what do you think here? Comment in the comment box. Mass and energy, both, do you feel that both are same, or do you think that there is a small difference? And if you find any difference, you tell me what is the difference. So here this nuclear force binds the protons and neutrons inside the nucleus. So how to calculate the mass defect? So there is a mathematical relation. This is the mathematical relation that we follow to calculate the mass defect of any atom. So if you take any atom or ion or molecule, the actual mass and theoretical mass have always been, there will be a difference between them. Okay, Z atomic number, mass of proton, mass number minus atomic number will actually gives number of neutrons. A minus Z gives number of neutrons. So mass of neutron, this total, if you observe this one, this will give the mass of the nucleus. This is theoretical mass of the nucleus. M, this is actual mass of the nucleus. Actual mass of the nucleus. When you are subtracting actual mass from theoretical mass, you will get the mass difference, that is called mass defect. So by this we can say that actual mass is always less than the theoretical mass. Why? Because that mass which is having a difference is converted into energy, in this case which is called binding energy, and this energy is spent to push the protons and neutrons in such a confined space together. So this nuclear force is very short range force, and now we see some details as per the binding energy and mass number. Before that, we will see what is binding energy per nucleon. Binding energy per nucleon. So this binding energy is a good concept to understand how strongly is the nucleons are bound in the nucleus, and if some two nuclei are merged together, there is some enormous amount of energy will be released, and to merge some protons and neutrons inside a nucleus also, we need to give the energy called binding energy, and the nucleus can be split into its constituents nucleons by giving the energy, that is called binding energy, EB. So when binding energy is divided with the mass number, it gives binding energy per nucleon. Binding energy per nucleon. So on an average, the binding energy per nucleon, when you consider all the atoms and take an average, it will be around 8 million electron volts. Okay, so this binding energy per nucleon also suggests that how strongly the nucleus is built up with protons and neutrons, and how much energy is we need to give to break the nucleus into constituents nucleons. We cannot simply just like that, we cannot split the nucleus, there are some processes. So we have an observation by drawing a graph between mass number and binding energy per nucleon. This is 50, 100, 150, 200, that is mass number, and if you consider from 0 to 4, 6, 8, this is given in million electron volts. Okay, so if you observe this, see, from 30 to 170, the binding energy per nucleon is almost constant. The binding energy per nucleon is almost constant. So the highest value it is reaching is, you can see, 8.75 million electron volts. For the mass number 56, it has gone up to maximum 8.75 million electron volts, and from here it is coming down up to here, that is for the mass number 238, it has come to be 7.6 MeV. So between 30 and 170, this binding energy is almost constant. 30 means from here, see, from here to 170, we can take it up to here, 170. So this, from here to here, you can see there is not much change in binding energy per nucleon. So what we can conclude with this characteristic is that the force generated because of the binding energy, which is called nuclear force, is a short range force and it is attractive force. Okay, so whenever a proton is surrounded by other protons inside the nucleus, because nuclear force is a short range force, it can act on the protons which are in the region of nuclear force. Other protons which are not in the region of nuclear force are not considered, and these protons will not be having any effect which are outside the region of nuclear force. So the protons which are surrounding a single proton will be having the attraction if they are within the region of nuclear force. Okay, so here there are some elements which are showing the binding energy per nucleon, and the characteristics we have studied here are valuable to understand the nuclear properties. The nucleus is stable or unstable. See, whenever the mass number of an atom is less than 30 and more than 170, the binding energy is very less. If the binding energy is less, means the nuclei is unstable. It is vulnerable to be splitted. So we can easily split. But between 30 and 170, we have a constant value, and more than 170 and below 30, the binding energy is less. So the maximum value is for 56. This value goes up to 8.75. On an average, we already told you the binding energy per nucleon is around 8 million electron volts. This is about the concept of binding energy. So we will have a next topic in the next video.